In this video, we are going to data mine novel chart patterns with Python. I'll outline an approach to find high-performing patterns in the price structure on any market. The visualization you are seeing now is the current price structure pattern drawn in white. We will save and normalize each of these shapes, then group them into clusters to find recurring patterns in price structure. We will assess the future behavior of the market after these price structure patterns manifest to find profitable patterns. If you like more advanced algorithmic trading content like this, consider subscribing. There are three main steps in this approach. First, we build a dataset of price shapes. Then we cluster the dataset into groups of similar patterns. Then we assess and select the best patterns that tend to precede a move in the price. First, we need to build our dataset. In this example, we are finding 5 perceptually important points on the recent 24 candles of data. If you are unfamiliar with the perceptually important point algorithm, I cover it in detail in my chart pattern algorithms video, linked in the corner. But quickly, the perceptually important point algorithm always selects the first and last points on a section of data, then selects additional internal points by finding the point with the maximum distance from 2 adjacent selected points. I drew lines between the 5 points to make it a little easier to see, but these 5 points serve as a summary of the price action over the last 24 candles of data. This reduces dimensionality, which makes it much easier and faster for clustering algorithms or other algorithms to process. We compute the perceptually important points for each subsequence of 24 candles across the entire dataset and record them. We will cluster these subsequences to find similar groups. This idea originated in 2001 with the publication of this paper. You may have noticed earlier, but as this visualization runs, the pattern shape does not update with each new candle. There's an important reason for this. In 2003, this paper was published that critiqued the 2001 paper. It claimed subsequence clusters are meaningless. This paper goes into great detail, and it is worth reading if you're interested in pattern discovery for trading, but in short, adjacent subsequences are not unique. They have considerable overlap. This overlap causes trivial matches and causes the patterns found to be essentially random. The authors of the 2001 paper made an update to their method to prevent meaningless pattern discovery in this 2005 paper. This updated method is the one we will use. We compute the perceptually important points with a sliding window on the recent 24 candles, but only include it in the dataset if the internal perceptually important points are different from the last subsequence. This change causes each subsequence to be more unique and avoid trivial, meaningless clusterings. It also reduces the total amount of subsequences to cluster, which reduces the processing time, an added bonus. Let's look at the code for this. The code for the entire data mining process is managed by a class, pip pattern miner. We first load in some data from a CSV. We convert the prices to logarithmic prices. The class assumes that the prices are logarithmic, so this must be done. We get the closing price as an array. Then we create an instance of the class. It has 3 parameters: the number of perceptually important points, the lookback, which is the number of candles the pips will be found on, and the hold period. The hold period will be discussed more later, but it is how many candles a position will be held after a selected pattern is found. We pass our closing price array to the class's train function. The nreps parameter will be discussed later. Here is the init function of the class. It doesn't do anything but declare variables. The main thing of note for now is the input parameters are saved in these values. Here is the train function. We save the closing price array as data in the class. Then we call this function findUniquePatterns. This function handles the creation of the unique pip patterns, which we will cluster later. We will keep track of the coordinates of the last subsequence in this list. We loop through each candle in the dataset. We find the most recent section of the data and store it in this variable window. When we initiated the class, we set lookback to 24. So window contains the 24 most recent closing prices. We find the perceptually important points on the recent data. We update the x-coordinates of the perceptually important points to match the indices of the entire array. We loop through the internal perceptually important points, ignoring the first and last, and compare them to the last set found. If there is a difference found, we set the boolean same to false and break. If the internal points are not the same, we record the perceptually important points as a unique pattern. We z-score normalize the price values by subtracting their mean and dividing by the standard deviation. This will cause each pattern to have a similar price scale, which allows us to cluster price patterns at different times throughout the data. We record our normalized pattern and the current index. Finally, we update the indices of the last found perceptually important points, then continue looping through the rest of the dataset. After we have done this, we have a collection of unique patterns the price has made throughout the data given. I should note that we do not pay attention to the time between the points making up the pattern, just the levels of price throughout the pattern. Now with our collection of normalized price patterns, we will cluster them into similar groups. There is a large variety of clustering algorithms, each with its own merits and weaknesses. But one important feature we need is the ability to classify new observations into a cluster. This way we can use the found patterns on out-of-sample data. I'm going to elect to use the simple, well-known k-means clustering. This algorithm clusters data into a set number of clusters. The cluster centers are the mean values of all the samples within a cluster. New samples can be assigned to a cluster by finding the cluster center that is the closest to it. I won't cover the algorithm here, but there are many resources available online explaining it if you are unfamiliar. When clustering these pattern shapes with the k-means algorithm, we have an important decision to make. How many clusters do we use? If we use less clusters, then the amount of price shapes in each cluster will be higher, which allows us to have a higher sample size and thus higher confidence when we assess the performance of the cluster of price shapes. However, using less clusters will group price shapes that are less similar, so we may miss out on a truly good pattern that exists but is lumped in with less salient price shapes. There is no perfect solution to this problem, and it is certainly something requiring further research, but a decent approach I've found is using the silhouette method. The silhouette method scores each sample for how well it fits into its cluster. Samples that fit nicely toward the center of their cluster score high, while samples that are on the outer edge, lying in between two clusters, will get a lower score. The silhouette score can be averaged across all samples, and this gives us an idea of how well the clustering performs. By using this method, we can compare the silhouette score when using k-means with 5 clusters versus 10 clusters, and select the better performing amount of clusters. I'll leave the citation for the silhouette method in the description if you want more detail, but thankfully there is a Python library to do the work for us, so let's look at the code for clustering. To do the clustering, we will use the PyClustering library. These are the imports that we need. This is the same train function we saw earlier. After finding the unique perceptually important point patterns, we use the silhouette k-search to try different amounts of clusters. I have it set to try 5 clusters up to 40 clusters. We get the best amount of clusters from the silhouette search. Then we call the function k-means cluster with the amount the silhouette method deemed best. The k-means clustering algorithm needs initial cluster centers to start the optimization. We get the initial centers with the k-means++ initializer. Then we pass the initial clusters and the unique pip patterns to the k-means instance and process. We get the cluster centers and cluster membership of each sample in the dataset. At this point, the price shapes are placed into clusters. Now we assess the clusters and select the ones that precede movements in price. To assess the performance of each cluster, I employ a simple holding period. Each time a pattern of a given cluster is found, we look at the market's price change over the next H candles. In the example we've used so far, we have found 5 perceptually important points on 24 candles of data. Since we are looking at patterns that span 24 candles, I think a natural holding period would be less than 24. I chose 6, as 1/4 of the pattern length seems like a reasonable prediction horizon. This choice is fairly arbitrary, but we have to pick something. Over the course of the training set, we will find the Martin ratio for each cluster. The Martin ratio is calculated by dividing the total return by the Ulcer index. The Ulcer index is calculated by summing the squared drawdown at each candle in the dataset. This causes the Martin ratio to be punished by both the length and depth of drawdowns. If a cluster of patterns have smaller drawdowns or recover quickly from drawdowns, then they will have a higher Martin ratio. The developer of the Martin ratio has an excellent article describing it in detail, which I link below. After we find the Martin ratio for each cluster, we will select the best pattern for trading long and the best pattern for trading short. We will combine the signals of the best long and short patterns, then compute the Martin ratio on the combined version. This will be our final performance figure. Let's look at the code for this. Back looking at the train function, I didn't mention this earlier, but at the start we compute the logarithmic returns of the closing price and shift them forward by 1 candle. We will use these returns in a moment. After clustering the patterns, we call the function getClusterSignals. And here's the function. We loop through each cluster found. For each cluster, we create a signal concurrent with the closing price array we passed in earlier. We initialize it as all zeros. We loop through each member of the cluster. We get the index in the closing price array that this cluster member or pattern happens. The index is the last candle in the pattern. We set the signal array to 1 for the set hold period. We used 6, so this will add 6 ones after this pattern occurred to the signal array. Then we add our signals to this list. It is a class variable. Back to the train function. After computing our cluster signals, we call the assign clusters function. We loop through each cluster. We multiply the cluster signal by the logarithmic returns. The cluster signal is composed of zeros and ones, so this gives us all the returns that a cluster was exposed to the market. We compute the Martin ratio from these returns. We'll look at this function in a second, but no, it returns a number. We record the Martin ratio for each cluster. After the loop, we find the cluster index of the highest Martin ratio. This is the best long pattern. Then we find the cluster index of the lowest Martin ratio. This will be our short pattern. We record the long and short pattern in these lists. I experimented with selecting multiple patterns, and I used a list to record the selected patterns. Here is the Martin ratio function. It is passed an array of log returns. We first sum the returns. If the sum is negative, we set this boolean as true, flagging for short trading, and we also flip the signs. We get the cumulative sum of returns. We exponentiate them for computing percentage drawdown. We also convert it to a pandas series to use the cumulative max function. In this line, we are dividing the current sum of returns by the max sum we've seen so far. We subtract 1 from this quotient. This gives us the percentage drawdown at each candle. We square this percentage and sum the squared percentage at each bar. This is the ulcer index. We complete the ulcer index by dividing by the size of the array and taking the square root. The Martin ratio is the total return divided by the ulcer index. If we flagged these returns as a short pattern earlier, we set the Martin ratio to negative. This way, the best long pattern will be the maximum value found, and the best short pattern will be the minimum value found. Back to the train function once more. We find our final Martin ratio with this function, get total performance. This function is built to handle selecting multiple long and short patterns if you want to experiment, but it works just fine with just the one selected here. We create a long and short signal of zeros for the length of the data. We loop through each cluster. If the cluster is a member of the selected long patterns, we add the cluster signal to the long signal. If the cluster is a member of the selected short patterns, we add the cluster signal to the short signal. We divide the signals by the number of selected patterns. In this case, it's just 1, so no effect. We multiply the short signal by -1 to flip the signs. We combine the signals by adding them. We multiply the combined signal by the returns. Then we pass these combined returns to the getMartin function we covered earlier. At this point, we found a pattern for trading long and a pattern for trading short from the data. Let's run this program on 2 years of hourly Bitcoin data, from the beginning of 2018 to the end of 2019. The silhouette method decided that 16 clusters was the best amount. Here are the cluster centers of the long and short patterns discovered. The long pattern is shown in green, while the short pattern is shown in red. Here is every member of the clusters found in the test period. The patterns are fairly loose. There is quite a bit of variation around the cluster centers. Here are the cumulative log returns of the long, short, and combined patterns on the in-sample data. They look pretty good, but these are in-sample results. We selected these patterns because they were the best, so there is a strong selection bias in these results. To compare the strength of the selection bias versus the strength of the actual patterns in the data, we will perform a Monte Carlo permutation test. To do this, we will permute the price returns to create a new permuted price path. This permuted price path has an identical return distribution, but all the legitimate patterns that may or may not be present on the actual path are destroyed. All that remains in the permuted price path is noise. We will run our entire procedure again on this permuted price path, build our unique perceptually important point patterns, cluster them, and select the best performing clusters. We will compare the Martin ratio we find on the permuted path to the one we found on the actual price path. If the result we find on the permuted price path is weaker than what we find on the actual price path, then that serves as evidence that there are legitimate patterns in the actual data. The more times we permute the price and do this test, the more evidence we gain. I generated 100 permutations of the price from the start of 2018 to the end of 2019, and found the Martin ratio for each of them. Here are the Monte Carlo test results. The Martin ratios found on each of the permutations is displayed as a histogram, while the Martin ratio on the actual price is displayed as a red line. The actual data is ahead of all the permutations. This is good evidence that there is something present in the actual data that is not present in the price permutations. Let's look at the code for the Monte Carlo test. The Monte Carlo permutation function is controlled by this parameter, n reps, the number of Monte Carlo repetitions we will use. It defaults to -1, which means we don't do the Monte Carlo test. After we have finished the entire procedure on real data, we are left with the final Martin ratio of the combined best long and short pattern. We save this in the variable fit Martin. We return here if the Monte Carlo test is disabled. We loop for each of the repetitions requested. These two lines shuffle the log returns of the original data. We concatenate the first value of the original array and the shuffled returns. We set the class variable data as the cumulative sum of the shuffled returns. Now we do everything exactly the same as we did before, but this time we are using permuted data. We find the unique pip patterns, cluster them, find the cluster signals, select the best, then we get our final performance figure on the permuted data. This is what we compare to the performance figure found on real data. We save this performance figure from the permuted data into this list. We've seen that our data mining process is finding something stronger on real data than it finds on noise or permuted data. So at this point, we'll try using our found patterns on out-of-sample data. We will use a walk-forward test to see if our patterns work on out-of-sample data. I'll again use hourly Bitcoin data, but from the beginning of 2018 to the end of 2022. We will train on 2 years of data and test on 1 year of data. So in this case, finding patterns with 2018 and 2019 data, then testing them on 2020, then training on 2019 and 2020, and testing on 2021, and so on. Let's look at the code for this, and then I'll show the results. Before we go over the walk-forward code, there is one more function we need to go over in the pip pattern miner class, the class we've been looking at so far. This function, predict, is for out-of-sample use. It takes a list of perceptually important points as input. We z-score normalize the input, then we loop through all the cluster centers and find the cluster center that is the closest to the input. This line here finds the Euclidean distance between the input and the center. If the closest center is one of the selected long patterns, we return 1. If the closest center is one of the short patterns, we return -1. Otherwise, we return 0. Here is the script for the walk-forward test. We load data in from a CSV, then convert the data into logarithmic prices. We get the closing price array. We create an instance of this class, WF pip miner, which is short for walk-forward perceptually important point miner. We will look at this class in a second, but we pass in the parameters for the pattern mining. npips, look back, and hold period we have already discussed. The train size is set to 2 years in hourly data, and the step size is set to 1 year in hourly data. We create a signal list of zeros, the same size as the array. We loop through each index in the array and call the class's updateSignal method to fill out our signal list. This function returns the current signal for that index in the array. After the loop, we add the signal to the data frame, compute the next returns, and multiply the signal by the returns to get the out-of-sample returns. Let's look at the class. In the initialize function, we save our inputs into class variables. Next train is the index of the closing price array when we will find the patterns. These variables hold the current signal and hold period of the system. We create an instance of the pip pattern miner class, which we already went over with the inputs specified. The class has only one function, updateSignal. We already saw the loop that uses it. We check if the current index is equal to the next train variable. If it is, we call the train function of the pattern mining class. We update the next train variable by adding the step size. We keep track of the hold period and signal with these two if statements. If the current hold period is above 1, we decrement. If the hold period is 0, we set the current signal to 0. At each index, we find the current perceptually important points. We pass the y values of the points into the predict function. The predict function returns 0, 1, or -1. If the return value is not 0, we set the current signal and set the hold period to the value specified, then return the current signal. Here are the out-of-sample results. This is the cumulative log returns from the walk-forward code we just saw. It is the combined performance of both long and short patterns found. We can see that the patterns found on 2018 and 2019 did very well throughout 2020, but the performance decayed afterward, essentially flat. It seems the patterns found in prior data did not continue to work into 2021 and 2022, but the performance of 2020 shows this type of strategy has some potential. What we did in this video is find similar structures in price and attempt to build trading patterns from them. What I showed only scratches the surface of what is possible. The code shown should be viewed more as a toy than a fully fledged trading system. It has a long way to go. The results are not stellar, but I wanted to show a complete example of pattern mining. A major issue with this implementation is the clustering is highly dependent on the random seed. It will return different clusters each run. This randomness is from the initialization of the clusters. Solving for the optimal k-means is an NP-hard problem, and what we actually get is only a local optimum. Also, each portion of the algorithm has plenty of room for improvement. We could better represent the patterns, we could find a better way to cluster, or even skip the clusters and do a nearest neighbor approach. We could also evaluate the patterns differently, beyond a simple hold period. But hopefully this video gives you some ideas for your own trading and research. I would like to make more videos on this topic in the future. There is quite a bit to be done. That's it for this one. Thank you for watching.